Wandering magnetic field. This is an illustration of our planet. What we wish to learn is, why is the axis of spin, that which the Earth spins about, different from the magnetic north and the magnetic south, which pass through our planet? The magnetic north is about 1,200 miles from the axis of spin, and it's in northern Canada. In the southern hemisphere, the magnetic south is at the rim of Antarctica. The magnetic field of our planet is formed through Earth's equator. As our planet spins, it generates what is known as the Coriolis effect. Winds in the southern hemisphere move differently than they do in the opposite hemisphere. This causes a shearing action through our equator. The energy of rotation in the southern hemisphere is opposite that of the northern hemisphere. A shearing action through the plasma area of Earth and the plasma area of a planet being that area where electrons no longer associate with any particular atom but are free to move about like in a soup. When there's a shearing action in a material like this, it generates an electric field. And when an electric field is generated, a magnetic field automatically is generated at right angles to it. So we can see that as the electric field is generated through the plane of our equator, the magnetic fields automatically form in the north and the southern hemispheres. That's the reason they form. What I wish to look at next is the density of materials. At 22 miles beneath our planet is the Mohorovic discontinuity. Mass in that area is thought to be generally at 2.8 grams per cubic centimeter. 1,800 miles from the center of our planet is the Gutenberg discontinuity, and it jumps to 6 grams per cubic centimeter. The density increases because the gravitational force increases in this area, and as the force increases, it compacts the mass. This is planet Earth. Notice the acceleration values. 1,500 miles from the center of our planet, mass is accelerating at 224 feet per second. If you were to release a mass in this area and it would fall freely, this is how far it would fall in 1 second. At 10 miles from the center of the Earth, notice how it jumps up. Instead of feet per second, it's miles per second, almost 1,000 miles per second. Then at 0.717 miles from the center of our planet, it is almost to the speed of light. If mass were released at 0.717 miles from the center of our planet, about 3/4 of a mile, it would be almost moving at the speed of light in 1 second. It's about 25 miles away from that of the speed of light. This shows how the mass must be compacted in these areas. Notice now the number 5,509. That's how many radiuses there would be within our planet. This is a radius where mass cannot exist because it would exceed the speed of light. It's the diameter. There would be 5,509 of these in the radius of our planet. So you can see that that area cannot be graphically drawn because it's too small. It wouldn't even be able to be seen if it were drawn to scale. Because of the density of the mass in this area. Magnetic lines cannot go through that dense material. Because it doesn't have the ability to go through that dense material, it moves over. The magnetic north and the magnetic south, this line should pass through the center of our Earth, but it has to move over because these lines cannot pass through this area where the mass is so dense. Magnetic domains cannot form there. Now, consider this to be a single bar magnet, North Pole, South Pole. If we were to take this magnet and divide it in two, through its center, you would have two small magnets, north-south, north-south. It wouldn't be north, nothing, and nothing south, but it would become two distinct separate magnets. Whenever you break a magnet in half, it will always form another set of magnets. The magnetic construction within the magnet is destroyed once it's broken. That happens in the magnetic pole running through our planet. This cannot be broken, otherwise it would become two magnetic fields. It has to move over in order to remain as one magnetic continuous line having a south pole and a north pole. This line of magnetism rides on the center area of our planet where the mass is so dense. It doesn't pass through it. It's like a teeter-totter. It's moving on the edge of it, where this field would be actually more dense in this area, moving outward. The lines of magnetism. Anyway, that's the way it appears. But we can see from this why that there is a wandering magnetic field within our planet.